a fantastic set of slides here.
Yeah.
Ready to unpack all the juicy details about these rocks, their formation, their unique personalities, and what they reveal about our planet's history.
It's amazing to think that these rocks we see all around us, from mountains to countertops, were once fiery, molten masses deep within the Earth.
I mean, right? It's like holding a piece of Earth's fiery past in your hand.
Absolutely.
So the slides kick off by talking about how igneous rocks are classified.
Right.
Based on where they cool down.
Exactly.
Okay.
If you've got molten rock chilling out beneath the Earth's surface, cooling down slowly, you get intrusive rocks with those beautiful chunky crystals, like in granite.
Oh, okay.
But if that molten rock decides to make a dramatic surface appearance as lava, cooling down quickly, you get extrusive rocks, fine-grained, like our friend basalt.
So it's all about location, location, location.
Yes.
Even for rocks.
Even for rocks.
And speaking of basalt, there's a whole section here about how the Hawaiian Islands are basically a basalt paradise.
The Hawaiian Islands are a textbook example of how volcanic activity shapes our world.
Right.
They're formed over a hotspot where magma just keeps pushing up from the Earth's mantle.
Okay.
And as the Pacific plate drifts over this hotspot, it's like a conveyor belt, creating a chain of islands, with the oldest ones getting further and further away from the action.
That the islands are on a slow-motion road trip.
That's a great analogy.
Powered by molten rock.
Yeah.
That's such a cool visual.
Yeah.
But let's hop over to another rock star.
Okay.
Andesite.
Andesite.
The slides describe it as having this medium texture and a grayish vibe.
Andesite is found in some pretty dramatic places.
Oh, okay.
Like those towering volcanic arcs. Think the Andes Mountains.
Right.
The longest continental mountain range on Earth.
Wow.
It's a testament to the power of plate tectonics, with the Nazca plate diving under the South American plate.
Okay.
Creating the perfect recipe for andesite to form.
Wow, so andesite is like a geological souvenir.
Yeah.
This epic tectonic clash. Okay, next up we have rhyolite.
Okay.
Described as a light-colored rock formed from super thick lava.
Rhyolite is known for its explosive personality because that lava is so viscous.
Right.
It traps gases, building up pressure until, boom!
Yeah.
You get these spectacular eruptions.
Right.
And guess what? That same stickiness is what gives rhyolite its fine-grained texture. It's a quick cool down from molten to solid.
So it's all about the drama with rhyolite.
Yeah, you could say that.
Now let's shift gears to the granddaddy of intrusive rocks, granite.
Granite.
The slides highlight its coarse texture.
Yeah.
And how those mineral crystals are big enough to see with the naked eye.
Granite is the classic example of slow and steady wins the race, at least in the world of rocks. That slow cooling beneath the surface allows those beautiful large crystals to form, making it a favorite for everything from countertops to building facades.
Yeah.
It's both durable and aesthetically pleasing.
Okay, we've covered the rockstar lineup.
Right.
But the slides also delve into some of the unique textures and formations you can find in igneous rocks. The first one that caught my eye is porphyritic texture.
Porphyritic texture is like finding hidden treasure within a rock.
Oh.
You've got these larger crystals called phenocrysts embedded in a finer grained matrix.
Right.
It's a two-step cooling process.
Yeah.
A slow cool to make the big crystals, followed by a rapid chill for the finer background.
It's like those fancy chocolate chip cookies with those giant chocolate chunks.
I like that analogy.
But instead of sugary goodness, we've got geological history baked right in.
Exactly.
And then there are vesicular rocks.
Yes.
The ones with all the cool holes, like pumice.
Vesicular rocks are a reminder that gases play a big role in shaping these molten masterpieces.
Right.
Those holes, or vesicles, are actually frozen bowls from gases trapped in the cooling lava.
Huh, okay.
The size and number of those holes can tell us a lot about how quickly the lava cooled and how gassy it was.
It's amazing how something as simple as a hole can reveal so much about a rock's past.
It is.
Speaking of revealing, let's talk about pegmatites.
Oh, yeah.
The rocks that rock the bling with their giant crystals.
Pegmatites are like the rock collector's dream. We're talking crystals that can be massive, sometimes even meters in size.
Wow.
They form in the late stages of magma crystallization, where you get this rich cocktail of volatile compounds like water and fluorine, creating the perfect environment for those crystals to grow to epic proportions.
So it's not just about the cooling, but also about the special ingredients in that late-stage magma mix.
Exactly.
The slides also mention kimberlite.
Kimberlite.
That's the one with dot diamonds.
Ah, yes, kimberlite,
Yeah.
the rock that brings the bling. It's incredibly rare and forms deep within the Earth's mantle, carrying those precious diamonds up to the surface through these explosive eruptions.
Okay.
They come from depths of 150 to 450 kilometers,
Right.
where the pressure is so intense that it forces carbon atoms to bond in a super tight structure.
Right.
A diamond.
So we're talking about a rock that's literally traveled from the depths of the Earth to bring us those sparkly gems.
Yeah.
Now, we've talked about the final rock products, but how does this whole magma-making process get started?
Magma formation is a fascinating process driven by heat, pressure, and something called volatiles.
So?
Imagine the Earth's interior, where temperatures and pressures are sky high. Add in some water and other volatile compounds, and you've got the perfect recipe for rocks to start melting.
Oh, okay.
It's like a giant underground pressure cooker, transforming solid rock into a molten mass.
Okay, so the Earth's interior is basically a rock melting factory.
You could say that.
But the slides mention different ways this melting can happen. Decompression, heat transfer, and the addition of those volatiles you talked about.
Yeah.
Can you break those down for us?
Absolutely. Let's start with decompression melting.
Okay.
Imagine a rock deep underground under immense pressure. If that pressure suddenly drops, say at a mid-ocean ridge or a continental rift, the rock's melting point actually decreases, and bam, you get magma.
So it's not always about adding heat. Sometimes it's about taking away pressure.
Exactly.
That's mind-blowing.
Yeah.
What about heat transfer?
Think of it like this.
Okay.
You've got a hot blob of magma rising up from the depths of the Earth. As it moves upwards, it heats up the surrounding rocks.
Right.
And if things get hot enough, those rocks start to melt too. This often happens in subduction zones where one tectonic plate dives under another.
It's like the magma is on a mission to melt everything in its path.
It's a powerful force.
And then there are the volatiles, those sneaky little magma makers.
Volatiles like water and carbon dioxide are like the secret ingredient in the magma recipe.
Right.
They lower the melting point of rocks.
Okay.
So you can get melting even without cranking up the heat or decreasing the pressure. It's like adding salt to icy sidewalks to make them melt faster.
So those volatiles are like little melting ninjas working behind the scenes.
I like that.
But here's a question. Do all the minerals in a rock melt at the same time?
That's a great question. And the answer is no.
Okay.
Different minerals have different melting points.
Right.
So you often get something called partial melting. Think of it like melting a multi-flavored ice cream.
Okay.
Some flavors melt faster than others.
Yeah.
Creating a new melted mixture with a different flavor profile.
So it's not just about the ingredient, it's also about the order they melt in.
Exactly.
And that brings us to Bowen's reaction series, which the slides describe as a kind of roadmap for mineral crystallization from magma.
Bowen's reaction series is a brilliant model that explains how different minerals crystallize from cooling magma at different temperatures.
Okay.
As the magma cools.
Yeah.
It's like a dance with different minerals stepping onto the dance floor at different times.
So it's not just a random free-for-all. There's an order to this crystallization party.
Exactly.
Okay, cool.
And this series has two main branches. The discontinuous series and the continuous series.
Okay.
The discontinuous series is like a relay race with one mineral crystallizing, then reacting with the remaining magma to form a new mineral, and so on.
It's like a mineral chain reaction.
Yeah.
What about the continuous series?
The continuous series is a bit simpler.
Okay.
It involves plagioclase feldspar, which gradually changes its composition as the magma cools. It's like a smooth transition rather than a series of abrupt steps.
Okay, so we've got our magma, it's cooling down, minerals are crystallizing.
Yeah.
But wait, there's another process at play here. Fractional crystallization.
Right.
What's that all about?
Fractional crystallization is like sorting through a giant box of Legos.
Okay.
As magma cools and those early forming crystals solidify, they can sink to the bottom of the magma chamber because they're denser.
Right.
This changes the composition of the remaining magma,
Okay.
leading to an even greater diversity of igneous rocks.
So it's like removing certain Lego pieces from the box,
Exactly.
which changes what you can build with the remaining pieces.
Yeah.
I'm starting to see how all these processes work together to create this incredible variety of igneous rocks.
It's a beautiful interplay of heat, pressure, cooling rates, and mineral crystallization.
Wow.
And it's all happening deep within the Earth, hidden from our view, until those rocks are brought to the surface through uplift and erosion.
It's like a hidden world of rock formation.
It is.
And we're just getting glimpses of it through these amazing rocks.
Exactly.
Speaking of glimpses, the slides mention a connection between igneous rocks and plate tectonics. Can you elaborate on that?
Absolutely.
Okay.
Plate tectonics is the engine that drives the formation of many igneous rocks.
Right.
Think about where magma is generated. Mid-ocean ridges, subduction zones, hot spots.
Yeah.
These are all locations where tectonic plates are interacting,
Okay.
pulling apart, colliding, or sliding past each other.
So the dance of the tectonic plates is what sets the stage for these molten masterpieces to form.
Exactly.
Okay.
And by studying the distribution and types of igneous rocks around the world, we can piece together a story of how those plates have moved and interacted over millions of years.
It's like having a geological time machine.
It really is.
Wow.
Each igneous rock carries a record of its formation, telling a story of Earth's dynamic past.
Yeah.
And that's what makes geology so captivating.
Right.
It's a journey through time, uncovering the secrets of our planet.
It really is amazing to think that those seemingly ordinary rocks scattered around us have witnessed millions, even billions of years of Earth's history.
Yeah.
They've been through volcanic eruptions, mountain building events, and the slow, relentless forces of erosion.
It's incredible.
And they hold clues to not only Earth's past, but also its future.
Right?
Remember those pegmatites we talked about with their giant crystals?
Yes.
They're a source of lithium, a crucial element for batteries, powering everything from electric cars to smartphones.
Absolutely.
As we transition to a more sustainable future, the demand for these igneous-derived resources will only increase.
It will.
That's a great point. So these rocks aren't just geological wonders.
Oh, right.
They're also key players in our modern economy and our quest for a greener future.
I agree.
And let's not forget about their role in construction. Granite, with its durability and beauty, is a mainstay in buildings and monuments.
Yeah, absolutely.
Basalt, on the other hand, is crushed and used in road construction and concrete.
Yeah.
Igneous rocks are quite literally the foundation of our civilization.
They are.
It's incredible how something that seems so ancient and unchanging is so deeply intertwined with our modern lives.
It really is.
You know, we've talked extensively about how igneous rocks form from cooling magma and lava. But I always wondered about those gases trapped within the molten rock.
Yeah.
What happens to them?
That's a question that often sparks curiosity.
Right.
Those dissolved gases, the volatiles, play a fascinating role in volcanic eruptions.
Okay.
As magma rises towards the surface, the pressure decreases, and these gases start to come out of solution. Think of it like opening a bottle of soda.
Okay.
The release of pressure allows the carbon dioxide bubbles to escape.
Okay, so the magma is like a giant bottle of fizzy rock.
That's a good analogy.
What happens to those escaping gases?
Well, it depends on the type of magma.
Okay.
If it's viscous, like rhyolite, those gases can get trapped,
Right.
building up pressure until they're released in a dramatic explosive eruption.
So it's the trapped gases that give those rhyolite eruptions their explosive power.
Exactly.
What about less viscous magma like basalt?
In those cases,
Yeah.
the gases escape more easily,
Right.
resulting in gentler lava flows. Think of the Hawaiian volcanoes with their slow-moving rivers of molten rock.
Yeah.
It's a visual spectacle, but far less explosive than those rhyolite eruptions.
So the viscosity of the magma and the behavior of those volatiles really determine the personality of a volcanic eruption.
They do.
Who knew there was so much drama happening beneath the surface of our planet?
It's a fascinating world down there.
So the viscosity of the magma and the behavior of those volatiles really determine the personality of a volcanic eruption.
They do.
Who knew there was so much drama happening beneath the surface of our planet?
It's a fascinating world down there. It's a constant interplay of forces and processes, shaping and reshaping our world over millions of years. Igneous rocks are a testament to that power, reminding us of the dynamic forces that have shaped and continue to shape our planet.
Right.
This deep dive has been an eye-opening experience, revealing the hidden stories behind those seemingly ordinary rocks we encounter every day. It's made me realize that even a simple walk down the street can be a geological adventure.
Absolutely. Every rock has a story to tell, a tale of fire and pressure cooling and crystallization. So next time you see a rock, take a moment to appreciate its journey and the incredible forces that brought it to your feet.
That's a perfect note to end on. We hope you've enjoyed this deep dive into the world of igneous rocks. And remember, the exploration doesn't end here. Keep your curiosity alive, keep asking questions, and keep discovering the wonders of our amazing planet.
Until next time, happy rock hunting.
It's a constant interplay of forces and processes
Right.
shaping and reshaping our world over millions of years.
Yeah.
Igneous rocks are a testament to that power.
They are.
Reminding us of the dynamic forces that have shaped and continue to shape our planet.
It's true.
This deep dive has been an eye-opening experience.
Yeah.
Revealing the hidden stories behind those seemingly ordinary rocks
Right.
we encounter every day. It's made me realize that even a simple walk down the street can be a geological adventure.
Absolutely.
Yeah?
Every rock has a story to tell.
Right.
A tale of fire and pressure, cooling and crystallization.
Right.
So next time you see a rock, take a moment to appreciate its journey
Yeah.
and the incredible forces that brought it to your feet.
That's a perfect note to end on.
Yeah,
We hope you've enjoyed this deep dive into the world of igneous rocks.
I hope so.
And remember, the exploration doesn't end here.
No.
Keep your curiosity alive.
Absolutely.
Keep asking questions.
Yeah.
And keep discovering the wonders of our amazing planet.
It's a great big world out there.
Until next time,
Yeah.
happy rock hunting.
Happy rock hunting.